Hello, everybody. Welcome back. So today we will keep on a great discussion of the matrix exponentiation. And if y'all recall the last video, what we did is we say that P is a collection of eigenvectors belongs to A. We did that through a series of assumptions. First, we assume P is a collection of alpha, which alpha is like the column vectors. And after some techniques, some multiplication, we come up to the fact that we have a series of A alpha 1 equal lambda 1 alpha 1, A alpha 2 equal lambda 2 alpha 2, and all that. So we can conclude that alpha is actually an eigenvectors, and P is a collection of eigenvectors belong to A. So now, since we have noticed, we can actually determine how to find the eigenvectors belong to A, and then that is going to be our P. Okay, so let me write down. My bad, I apologize. Let me go ahead and do this. So now you write. So now, how can we find the eigenvector of A? Okay, because if we can find the eigenvectors of A, then we obtain P. So let's go ahead and go back to our definition of eigenvectors. So what is our definition for eigenvectors? So an eigenvector of A, let me do this so it's kind of organized. So if you all recall, the eigenvectors of A is defined as V, such that, okay, V, I will write a vector, so I'm not going to write the circular form, because usually the standard form is easier to recognize for y'all, so I'm going to write like this. So, V such what? So, it's such that you can scale that vector using a matrix A, into a. Let me write on and I can explain for y'all. So basically, it means that you can apply you can scale a matrix A. You can use a matrix A, okay, to scale that vector. To scale down that vectors. Okay, yeah. So this is the mathematical definition. Okay, so where lambda is a scalar, and A is a matrix, and V is a vector. And all the V value you can find later is gonna be your eigenvectors. Okay. So, but before finding eigenvectors, we need to find the eigenvalue. So how do we do that? So let's go ahead and manipulate this expression. So what I'm going to do is I'm going to do something like this. So I would say AV equal I lambda V. Okay, what is I? I is the identity matrix. Okay, because the reason why is you apply the identity matrix to a vector, you get the same vectors, but we need the dimension to be similar. Okay, so what you're gonna do is you're gonna write something like this. So AV minus I lambda V equal 0. Okay, so or in another word, A minus I lambda by 2V equal 0. Okay, so this is a very, very interesting observation right here. Okay, so what does it say is that you have a matrix A minus I lambda. You apply that matrix onto a vector V, and you get a zero vector. What does it mean? Again, I'm gonna referring back to 3 blue 1 brown. Okay, so according, let me write. What does this mean? So what does it mean? So according to 3 blue 1 brown video, and what's that video is called eigenvectors and eigenvalue video. The only way to apply matrix transformation in this case is our I minus I lambda to this is, be careful, non-zero vector V results in 0. The transformation must squeeze the vector into a lower dimension in order for that to happen. The determinant must equal 0. Okay, let me explain what I write. Okay, so basically when y'all look at this, what are you doing is you applying transformation or a matrix, which is in this case A minus I lambda into vector V, and you squeeze it down to 0. Okay, so usually what happens is you apply a matrix to a vectors, it results in another vectors same dimension. That's the most common case, instead of like 0. So 0 is a special case, right? So it's a special case happens. So the determinant have to become 0. Okay, so that it can squeeze V to lower dimensions. Okay. So what you can say is so if determinant equals 0, what does it mean? It means that the determinant of A minus I lambda equals 0. Oh, you can also watch 3 blue 1 brown video on determinant too. Let me see. Well, that's a very interesting color. Let me try this. Also watch 3 blue 1 brown video on determinant. Okay, so let's go ahead and so the determinant equals 0. Okay, so you can definitely obtain on the lambda 1 here. So so if you solve for determinant, which you can watch in details in the videos in Khan Academy also, you can solve for, you can obtain all of the eigenvalues. What's the eigenvalue? So what I mean is lambda 1, lambda 2, all the way to lambda n. Okay, and then you can get the eigenvectors. The way to get an eigenvectors in details is after you get an eigenvalue. Okay, so as like for example, let's say you want to get eigenvector v1 from lambda 1. How do you do? So what you can do is you can plug lambda 1 back to the original equation, this one right here, a minus I lambda v equals 0. So you can plug it back. You can say a minus I lambda 1 v1 equal 0. And from there you can obtain v1. Okay, and after you get v1, v2, all of that to vn, all the way to Vietnam, you can obtain p, because remember p is a collection of the eigenvectors Vito. So eigenvectors. Okay, you can obtain p. And that is it. That's how you get p. So in the next video, I think that's good for now. So in this case, all I'm trying to demonstrate to y'all is P is actually a collection of eigenvectors, and this is how you get the eigenvectors. Some intuition behind it. Okay, so in the next video, I will try to expand the rest and see what we got. Thank you.